Okay, so we're back again, and if you're watching this, hopefully that means that you've completed the data analysis activity for the photoelectric effect, and have seen some patterns. So just to recap a little bit, what we have is a situation where we have this wave model of light, which gives us two parameters that we can vary. We can vary the intensity of the light, which is how hard is the electromagnetic wave going to shake electrons attached to an atom. And we can vary the frequency of the light, which is how fast does that shaking take place. The conceptual model that we have for the photoelectric effect is that this wave comes along, it shakes the electrons either at some intensity and some frequency. That deposits some energy in there, the energy builds up, and eventually the electron collects enough energy that it pops out, and that's what we see in the photoelectric effect. The experiments we can do, there are two experiments that you can do with the photoelectric effect. One is to measure how many electrons per second are ejected based on the light that you're shining in. And the second experiment is to measure a voltage that tells you what is the maximum energy of an electron that's been ejected by that light. So we've got two parameters that we can vary. We've got two experiments that we can do. That gives us sort of a grid of four possible experimental configurations. We asked you to make some predictions about this, thinking about the wave model, and there's four predictions that we have. The first is that the number of electrons per second that come out should increase as you increase the intensity of the wave, right? If you shake something more violently, then you should get more electrons out. The second prediction is that the energy of the electrons that come out ought to depend on the intensity in the same way. If you're shaking it harder, they're going to pick up energy so fast that they're going to come out with a bunch of extra energy. As far as how the number of electrons per second and the maximum energy should depend on the frequency, that's not so clear. It's not really obvious that there should be any simple pattern to how the electrons are emitted that depends on the frequency. So, maybe there's some special frequencies where they come out really easily. Maybe there's not. There's all sorts of possibilities. It's really not clear what to expect for either the number or the energy of the electrons as a function of the frequency. So this is the situation in the early 1900s. Physicists went and looked at this and did some experiments, and what they saw is pretty much what's summarized in the spreadsheet that you had to analyze. So for this, we'll go through kind of what did we see in those spreadsheets. So the first and most straightforward of the predictions is that the number of electrons that come out per second ought to increase as you increase the intensity. And when we look at the data, that's in fact what we see. For 5 of the 7 wavelengths that we measured here, we see that there is an increasing current as we increase the intensity in the of the light. And that's exactly what we expect. But there's this one weird little note, which is there's these two points, the two longest wavelengths in the data set did not show any increase in current. In fact, they showed basically zero current no matter what the intensity was. So that's a strange thing, and put a pin in that for later. But in a general way, we can say that when we are getting electrons out, the electrons behave like we think. If we increase the intensity, we get more electrons per second coming out, as long as we get any electrons coming out at all. So the second most straightforward prediction is that the energy of the electrons ought to increase as we increase the intensity. So we can go and look at that, and here's a graph showing that for the simulated data, and that's not what happens here. Right? We look at this, we see that the energy, it bounces around a little bit because there's some random noise in the data that we have. But really, there isn't a pattern at all. The energy is pretty much constant for whatever intensity we put in. So that one we have no choice but to chalk up as a complete failure of the wave model. Right? The wave model says we should be accumulating energy, and we would think that if we're shaking the thing more violently, that should lead to higher energy of the electrons coming out. But in fact, that's not what we have. What we have is a constant voltage, the same energy, same maximum energy, no matter what the intensity is. So that's really weird. So now we turn to the two cases that the predictions were kind of ambiguous. One of these is the energy as a function of frequency, and here what we see is something like this. This is showing all 5 intensities that we look at, and showing the energy of the electrons on the vertical axis versus the frequency of the light on the horizontal axis. And what we see is a pretty simple pattern. This is surprisingly simple, right? We thought there might be something weird that happens, but actually what we see is really pretty much a nice straight line with a kink in it, right? Those first 2 points, we really don't have any voltage at all there. What we see there is pretty much just the noise. And then above that point, we have a nice linear increase in the energy as the frequency increases. It's a nice straight line. So that's way simpler than we thought it should be, right? That's kind of a strange feature. Also, the fact that there is absolutely no emission. There's no stopping potential, no electrons coming out for very low frequencies. That's also a surprising feature, and that's something that we saw earlier in the data when we were looking at the current as a function of intensity. We saw that for the longest wavelengths, there was just no current ever, right? There were never any electrons coming out. So that's kind of striking and interesting. The last possibility for the experimental configurations is to look at the current as a function of the frequency. And again, here we see a very simple pattern with a sharp break in it. Right? For the lowest frequency points, as before, we just get no current at all. And then above that sort of cutoff frequency, what we see is a linear decrease in the current as the frequency increases. Right? We see nice straight lines above some point, and those straight lines slope sort of downward. So again, a very simple pattern shared across all of these different intensities that we have, but not the sort of thing we would have expected. We would have thought that there might be something weird and complicated going on here. So if we're evaluating the results of our predictions, you really can't say that either of the frequency dependence things is a success of the model. Right? We see a very simple universal pattern here, that there is a cutoff frequency, and below that we have no emission of electrons at all. Above that, as we increase the frequency, we get higher energy in a straight line sort of way, and we get fewer electrons coming out, again in a very linear fashion. So this is weird, right? So the photoelectric effect seems like something that ought to be really simple. We have this conceptual model for what's going on here, and it just really just doesn't work at all, right? 3 of the 4 possibilities that we had, 3 of the 4 cases that we could make simple intuitive predictions for, just doesn't work at all, right? And 1 for 4 might let you stay in baseball for a little while, but it's really not good if you're a scientist. So there's a bit of an odd break here, which happened because I ran through the wrap-up of the photoelectric effect in one really long continuous thing, and it turned out to be, probably a little longer than anyone's really going to want to watch as a video. So I'm splitting it into 2 pieces. So I broke the long thing in half, and we'll publish this little me talking at the end of the first half, and then I will do a little intro for the second half, and we'll run that at the start of the next one. So I'm going to break it into 2 videos so it's a little easier to be asynchronous and watch these conveniently without overstraining yourself. So that's what's happening with the weird break. Look on Nexus for the next video.